to welcome Emilio Calvano here. For the presentation, he's an economist who's now in Rome, working on topics related to competition economics, industrialization, especially in digital markets. He got his PhD from Toulouse, and as said, after a couple of stops at different universities, he's now in Louis. And his work was published in various journals like Science, AR, Economic Journal, or Management Science, and is also, for instance, editor of the Journal of Industrial Economics. And so for me personally, and I think for many of you who know what I work on, sort of algorithmic pricing and inclusion, Emilio's work has been quite influential, I think, to kickstart his and with his co-authors, his work to kickstart like this trend in economics to look at like the possibility that algorithms can collude, so essentially cooperate in a market environment, which I think for those people here that come more from computer science background, essentially if you think about multi-agent reinforcement learning in like a strategic game with an application then of economic theory to understand it, to understand machine behavior, I think how many here would frame it. So I think this has been quite an intriguing work, and looking forward to the presentation here today about recommendation algorithms. Please, Emilio.
Thank you very much for the nice introduction. Thank you very much for having me here. I had such a blast. This is such an interesting place for me to be, precisely because I spent a few years thinking about how to bridge the gap between disciplines to try to make progress to the problem of figuring out what's the impact of these AI tools on markets and society at large. So let me borrow a few slides from a talk I gave 2 days ago in Barcelona, just to give you an idea of my own research agenda. Let me say up front that I welcome questions during the talk, and so feel free to clarifying or not. I'll keep up with the spirit of the seminar, which is I prepared a rather short presentation. So my talk in Pompeo was like 61 slides, and now I have 27 for today's talk. And now all of a sudden I wonder, maybe I left out something important from those slides. Hopefully not, but there's plenty of time kind of built in for discussion. So if you want, please engage. All right, so I've been thinking about these algorithms simply because firms, as you know, as you teach me, they've been increasingly designing and deploying AI-powered algorithms in actual marketplaces for quite some time now, and that's all. That was the case even before we had these foundation models, because many of these tools that were deployed were kind of crafted to crack particular problems. And so actually, my way of thinking about AI, and it's still largely like that, is that these are not sophisticated tools by any means. These are kind of blunt statistical models to make predictions. And then the question is, yes, on the one hand, they're a great source of surplus, but on the other hand, I'm a competition economist, so I think about ways that the deployment of these tools could lessen competition or harm consumers, and I'm trying, to inform a debate, a large policy debate about, potential issues and thinking about potential remedies to those issues. Okay.
Can I have a question here, because I've heard in economics you're supposed to jump just in there.
Yes.
So
it's that bad. It is that bad. Yeah.
So, for me, that seems like you're covering one side of AI, right? Like supervised machine learning. You're not covering reinforcement learning, which we just have heard like a second before. So is this like that you're saying like this talk is about that side of AI, or would you actually say reinforcement learning under this?
Yeah, in my research agenda, I've been using a set of tools, including reinforcement learning tools. So the work that Tobias mentioned is basically showing that you can train RL algos to price goods, and thinking about whether the fact that these algos interact in marketplaces could lead to suboptimal outcomes, such as higher prices. Okay, so thinking about reinforcement learning to defy competition. Okay, Today's talk is more of the machine learning kind of spirit, in the sense that we're going to use some data to make predictions, and then we're going to use those predictions to shape consumer choices and firms' incentives. So you know, I'm trying to contribute to both these. Yeah, so I like this this kind of comment, because it's kind of shows where we were before AI. You know, the basic difference between this and now is that now that dog, is that a dog? That dog is now an AI tool, which is autonomously learning how to exploit, say, things like behavioral biases, or you could even think it's autonomously learn how to maximize some objective function, which might not coincide with the one of those, you know, guys who have to click or not. Okay, and you know, and this is legal, right? There is this kind of big question mark, which is, shall we pretend that, you know, this is all okay? Right. But so, as I was mentioning, there are many applications that's are not least, but you know, we kind of interact with these tools on a daily basis. And then the question is, as an economist, you know, how you know, can I contribute, right, to studying the impact of these tools on markets? And here I want to step back for a second and make a methodological point. So the idea is, how would you do this? I'm a theorist, an applied theorist. So at the very beginning, I remember when we were thinking about pricing tools, we were wondering maybe we should try to do this in theory. Okay, so we should write a model that is trying to understand what is the kind of long run outcome of a repeated interaction between AI agents. Okay, so I learned a lesson which is crystal clear to anyone who's done a bit of physics in their life, which is, if you take simple algorithms and you let interact for a long time, they give rise to complex systems which are basically untractable. So even the simplest ones kind of are untractable. So the next thing that you could do is, of course, if you have rich data, you could try to kind of do empirics, or you could do experiments. So this is what I started doing. I started a research line in which I ran either synthetic experiments or field experiments to answer this question. So today is going to be a synthetic experiment, or a simulation, or a computer simulation, whatever you want to call it. And so the idea is, so we're going to operate actual AI tools, simple ones, but actual AI tools in synthetic and controlled environments. The nice thing is, by synthetic, I mean that these tools, they're going to interact in a fake world, okay, which is designed by me, the economist, trying to capture the essence of the problem at hand. And is going to be controlled in the sense that the nice feature about having these tools, you know, run in simulations is that you can control things such as, you know, the quality of the data you're feeding to the algo. So you can actually hope to answer the question, which is, you know, if there is a suboptimal outcome, is it a data issue? Is it an algorithm issue? Is it both? And things like that. So you control everything. So you have what I call perfect identification in synthetic environment. Now, of course, when you try to sell this, you know, anyone who's tried to sell this to the profession would face two challenges, which have to do with external validity, right? Emilio, what do you know about algorithms, right? Second, Emilio, what do you know about, you know, creating good synthetic replicas of actual market settings? I would say that on count one, the idea is, you know, what I did was to study simple textbook versions, you know, things that I can understand. But eventually, the idea is to cooperate with computer scientists, okay, and with firms, if they allow us, to study the actual tools. And the second one, I would say there, you know, kind of put my foot down and I say, okay, so after years and years of kind of estimating models of marketplaces, we actually know how those marketplaces look like. So we're actually able to replicate those environments by kind of leveraging on what we found. All right, so the idea here is trying to provide a methodological contribution, which is, why don't we try and do these two things at once, so bridging econ and computer science to identify things. And second, yeah, of course, contribute to the specific debate. And today's specific debate is on recommender systems. Okay, so let me jump to the short version of this talk. All right, so I guess most of you, if not all, know what a recommender system is. But just to fix ideas, let me just mention that these are simple tools. Okay, these are simple tools. Was job, for me, through the lens of economics, would be they're trying to predict preferences. Okay, so you have some items, you have a set of agents, humans who have preferences over those items, and so the idea of recommender systems is to predict those preferences. Try and predict what these agents should consume out of this set of agents, and then to make recommendations based on those predictions. Okay, that's what they are. They are a remarkable and visible application of AI. They affect user choices. I will give you a few of my favorite examples in a second, and they have the attention of policymakers. Okay, so for instance, the Digital Service Act would define what the recommender system is, and if you read it, it would kind of prescribe, it would make prescriptions and things that firms should do to avoid that there are negative effects. Okay, and the policymaker is actually emphasizing this possibility that these effects, there could be side effects to the deployment of these tools, right? And my take is that the Digital Service Act is being enacted, is a law right now. The Commission is drafting the delegated acts. And I talked to these guys, and my take at the moment is that we're kind of flying blind. Like to answer these kind of questions, how to fix these recommender systems, we're kind of completely flying blind. Like we don't know. And so the idea was to try to inform this debate by running these simple experiments. Even these simple experiments, I think, can help inform that debate. Okay, so for the sake of this talk, I want you to, think of recommender systems in a particular context, which is a marketplace. Okay, so the idea being, I go, when I took this screenshot, I was visiting Berkeley, I was in the Bay Area, and of course, when I was looking for California travel guides, Amazon knew that I was, in San Francisco, and it would put like the Northern California guide on top of that. Maybe Amazon also knows that I have 2 kids, so I tend to like adventurous trips. I suppose I cannot afford the 3-star Michelin restaurants and things like that. So it would kind of avoid the foodie guides in favor of the more family-oriented guides and things like that, right? So this is what economists call personalized prominence. Okay, so the idea is that there is a number of, suppose I have a need, I have to buy a product. There are a number of substitute products that would satisfy that need. And then what Amazon is doing is choosing the one that is putting in front of me, the one that, if you want, they think I should be buying. Does that make sense? And of course, this page would look different, if you were to load it right now. And so that's why it's personalized. It's not just prominence, like when you go at the supermarket, you see some prominent stuff at the entrance, but it's personalized. Okay, so it's personalized prominence. So that's the mechanism. Of course, this is used across the board. These guys, they're the famous one. Those are the ones who developed the most sophisticated models early on. Netflix is a good example of a recommender system, which is shaping the kind of content that we consume. Right, and to the extent that you care about the content that we consume, if you're like me, you tend to watch what's in front of you, or you get frustrated because you don't find anything. So it's very important that this thing works. Spotify and so on are good examples. Okay, so the conceptual framework is very simple. So there is users, as they call them in CS, or consumers, as we call them in econ. These guys, and there are J firms, okay, those are the products, the number of varieties of travel guides that you have that are competing. So these are differentiated products. And let's assume for simplicity that, one firm, one product. And then UIJ is the utility that consumer I attaches to product J, or the match value if you want. These things are unknown, and also the price of those products are unknown, okay? And the idea is that we're going to contrast, that's very important, a world with no recommendations, okay, with a world with recommendations. And the goal of this exercise is to tell you what changes when I switch on those recommendations. Okay, that's the exercise. Now, in both worlds, at the beginning, consumers don't know what their preferences are and don't know what the prices are. In the world without recommendation, consumers, they have some technology to gather information, okay? So we call it costly sequential search is kind of a natural starting point. So the idea is that suppose I'm in a library, okay, and I just go towards the travel guide shelf, and then I pick one, I inspect it, I see if it is good, and then I have to decide if I want to waste, 1 more minute or 2 more minutes into inspecting a second one, or if this is good enough, right? And I keep doing that until I think that the value of searching more is lower than the value I would get if I were to buy the best product that I sampled so far. Okay, this in economics is like a standard benchmark. Consumers with no information, they typically have a search technology that allows them to gather information. Yes?
But the assumption is that without references, they are all individual searches. So
yes,
there's no information sharing.
No. No, you're right. So the world is more complicated than that. Now we could try and embed some spillover, some information. So now here I'm describing this exercise, right? And then maybe we can discuss variations on this theme that either would kind of challenge the claims that we make or that would be more interesting to study. I agree with you. The world is more complex than this.
Can I maybe also ask why you are assuming that the prices are known?
That's an excellent question. So you could do this exercise in 2 ways. Actually, these are 2 very different exercises. The first one is you assume that prices are not known, okay, to the consumer and to the algorithm. Okay, so in a way, the idea is that the algorithm is trying to match you with the best product, and so prices are kind of outside of the equation. Then you could do the exercise in which, say, consumers know prices and the algorithm knows prices, okay? And then that's a more complex exercise because then you would have to study a model in which this search is directed. So the idea being I'm more likely to sample lower price products, okay? And when you switch on the algorithm, the idea is that if I lower my price, it's more likely that the algorithm is going to put this product at the top of the search results pages. The point is that the point we try to make is that, first of all, these are 2 interesting exercises. We're going to do the second one, but when you keep bring prices into the equation, this effect, at least ex ante, will kind of wash out. In the sense that, when you're searching as a consumer, you're more likely to sample cheaper products. And when the algorithm is reacting to price, is more likely to put in front of you a cheaper product. And then the idea is that being cheaper kind of helps you, but we're looking at the difference and that washes out. So yeah, sorry for the long answer, but that's an important question. So yeah. Okay. So, okay, consumers have access to this search technology. And then on top, when we look at the treatment, when we switch on those recommendations, we're going to have in mind, say, a benevolent platform or a benevolent recommender system that is going to estimate those match values from some data, and then is going to use those estimates to direct search towards the stuff that you should be buying according to those estimates. Okay, so what I'm trying to rule out here is, this in the first part of this paper, we rule out a wedge in incentives. Okay, so the recommender has no incentive to divert me towards products which are more profitable. Okay, like clearly, if you think in an Amazon setting, if Amazon were selling a travel guide, he would have an incentive to put this stuff on top, right? Maybe because margins are fatter. Let's assume that away, and I will recover that at the very end of this talk. Okay. So there really, I would call the recommender system is not really a strategic agent. It's just a tool. It's estimating those use, and then it's using those use to put in front of consumers the highest rated items conditioned on the data that they have. Okay, so I'm interested in these kind of questions, which is whether these tools are anti or pro-competitive. Okay, so if you order Amazon to switch off those recommendations and say to order products at random within categories, is that going to induce? How's that going to shape consumption? Is that going to induce prices to go up or down? Is that going to make firms compete harder or not? Those are the kind of questions we're interested in. We're also looking at consumption diversity, right? Are those recommendations biased in a systematic way? Do they increase or decrease concentration? And of course, the idea is now put yourself in the shoes of firms. In a world with recommendations, firms, when they're making their strategic choices, they're going to take into account that those choices are going to be mediated by an algorithm. So the idea is, in the old world, firms were trying to persuade consumers to buy their goods. In the new world, firms are trying to persuade algorithms to put their stuff on top. And these two things are not necessarily the same. Okay, this is what we call algorithmic demand. So I want to show you how demand looks like with no recommendation relative to how demand looks like with recommendations. Okay, and looking at the difference is going to teach us a lesson about incentives of these firms. Okay. All right. So we do this by running those experiments that I already mentioned. So we're going to, this is kind of an elaborated exercise. So conceptually simple, but lots of moving parts. Okay. In the first part, I'm going to design, me, the researcher, consumer preferences over items. I'm going to create a bunch of synthetic consumers, and I will endow them with preferences that I design. So I get to choose what consumers care about. So that's going to be grounded in economic theory. Okay. I'm going to use like workhorse models of product differentiation from economic theory to design those preferences. Now that I have preferences, I know true preferences, I'm going to build a data set based on those true preferences, okay? And think about, say, I know all those match values. I know them because I designed them. Then I'm going to create a data set. You say, the simplest thing that we do in the baseline, we're going to have a random draw of those match values. It is as if, the algorithm is given a representative sample of those preferences, a representative and exogenous IID sample of those preferences. That's as good as it gets. But because we control everything, we could also build other kind of data sets. So one thing that we do is what we call the endogenous data treatment, in which rather than drawing from true preferences at random, we do this. Like we draw, so we start with the average utility. We train the system. It's going to make terrible recommendations because there is basically no data. And then consumers are going to make their choices. They're going to report their true match value to the system. Now we have some data. We retrain the system, right? We make recommendations. We look at choices. Consumers report, and we retrain the system, and we make recommendations. And so the idea here is to capture the fact that these kind of data sets might be biased because you get to only observe what people consume. So you're really drawing from the tails of the distribution. Now, you don't get to see a random draw, right? We tend to consume stuff that we like. And then the question is, the fact that these data sets have these characteristics, is that going to induce a bias in the kind of recommendations that we get? Does that make sense? Okay.
Can I ask that?
Yes.
So the correlation structure of the utilities is chosen in a specific way, or?
Yes, I think
you will. Okay.
Yeah. This is just an overview so that we are on board on what the exercise is, and then I'll give you some detail on this point. Okay. So now we have true preferences. We have data based on those true preferences, and then we're going to train a simple recommender systems to predict those preferences. That's kind of taken straight out of a popular textbook on recommender systems. Once we train that, the idea is that we're going to look at a world with recommendations that use those estimates and a world without those recommendations. Okay. Good. So the nice thing about this exercise is that we know everything, right? We know what should be consumed, we know what should be recommended, we know what people choose. So, you know, again, perfect identification, but in a synthetic environment. Okay. So this is the crash course. So I'll do this in steps. This is the algorithm. It's a simple one. This is the basic ingredient of a recommender system, which is called the rating matrix. This is literally a matrix in which you have items as columns, users as rows, and the idea is that you have a sparse matrix whose entry is the rating that user I gave to product J. Okay, so it's not actually the utility, right? So sometimes you get to observe the actual utility because maybe you ask, you ask the user to rate. Sometimes you have what is called implicit feedback. So for instance, Netflix, many years ago, they were actually asking you, I don't know if you remember, I'm old enough to remember when Netflix said, please rate this movie, rate this movie, rate this movie. Now they don't do that. They look at what you watch, they look at what you do, they look at whether you hit play and then you go back, and they record those as like feedback, and they populate this metrics. It's an art how to populate this metric. For the sake of this talk, the idea is that that's going to be the actual utility perturbed plus some noise. Okay, good. Typically, it's very sparse. Okay, so the ratio of observations to parameter is very, very small in this case. Now, the task is, if you have some data, the task is, of course, to predict the missing ratings. And so it's a matrix completion problem. It's a very standard problem. The kind of recommender we use is called the latent factor model. It's a collaborative filter of the latent factor class, And the idea of this algorithm is that the rating of kind of very familiar to economists, and it's actually very intuitive. So the idea is that the rating that user I attaches to item J is going to be an additive combination of K latent factors. Okay, so it's basically the dot product of two vectors. One is user specific, the other one is item specific. The way when I teach I/O, I say that the utility is basically going to be the dot product of product characteristics and tastes for those characteristics. So one way of thinking about it is, we have these sugar classic papers in demand estimation are about cereal boxes. So the idea is that suppose you want to estimate how much this individual likes this particular cereal box, then the idea is that the vector of B's captures things like sugar content. Okay, so every box of cereal is characterized by some fat, some sugar, some fiber, and so on and so forth, a vector of characteristics. The T vector is, Emilio tastes for sugar, fat, and so on and so forth. Okay, so it's kind of these algorithms, they embed some structure, okay, in preferences, right? They basically exploit correlations. So the way they can predict these preferences is by saying they exploit row and column correlations. So the idea is, I'll find somebody like Emilio, and then if Emilio likes something that Tobias, who's like Emilio, didn't try yet, then Tobias is likely to like that item. Right? So this is exploring similarity between users, and you could do the same by exploring similarities between items. So similar items like cereal boxes for kids tend to have, similar ratings, right? So adults hate them, kids love them, right? So that's the kind of correlation used. Then basically what these tools do, they estimate two vectors of parameters, user specific and product specific. Then they impute the missing entries. So you go from R, the data matrix, to R hat, the estimated rated. And then they just rank products according to this estimate, and they make recommendation based on that. Does that make sense? Okay. So that's the algorithm. Now, where are these preferences coming from? Well, in this exercise, we're going to use the exact same model to generate preferences. Okay, so I'm generating preferences that are the additive combination of k latent factors by design. So me, the designer, I have to choose those parameters. I literally have to pick those parameters. I have to pick a vector of tastes for each user, and I have to pick a vector of characteristics for each product. Okay. Now, how do you do that? Well, we're going to use simple workhorse models because we want to study how these tools work in very specific settings. One is called, so let me first of all give you a spatial analogy, which is the way, I think, the right way to think about this. So suppose there is some space, okay? So users are going to be placed in this space, okay? And products are going to be placed in this space, okay? And then the idea is that preferences of users are for proximity. So if I take one user, that user would prefer the product which is closer to him in that space, and the second best product would be the second most distant product, and so on and so forth. That's how you do this. This is called the Lancasterian model of product differentiation. We want to confine ourselves to a model in which preferences are purely horizontal. What does that mean? That, you know, if we were these users, we would all disagree on what the best product is. Okay, that's one extreme. We all have our own idiosyncratic preferences, and we would all disagree. I'm not saying that preferences are not correlated. Maybe me and Tobias, we disagree on what the best product is, but we're close in space. So, you know, what is first choice is also good for me. I would have a different first choice, but we're close in space, right? So you still have correlation between those preferences. A polar opposite case is a case in which preferences are vertical, as we call them. So we all agree on what the best product is, right? So there is one product which is better than the other. And we all recognize that. Okay, so clearly, if you think about prediction, the first problem is much harder than the second one. Because in the first problem, you know, you really have to figure out idiosyncratic preferences, although you have these correlations. In the second one, you just have to figure out what is the best product that everybody likes. So another thing that we inject by choosing those parameters is this idea that some products are more central than others. So that there are what we call mass products and niche products. Okay, so we define a mass product as a product with a larger potential demand. So a product which is placed in space where there are many users. Okay, right? And niche products are products which are placed in space where, you know, on average, you know, there are less users around. And then we want to see, you know, if these algorithms, they tend to favor mass over niche products. Okay, these are the two desiderata. Okay, I told you about the data, so we do this with. I'm going to show you just two treatments. The one with purely exogenous data, random draw from these preferences with the endogenous kind of process I described before. We also have all sorts of noisy data because the idea is I have true preferences, so you know, I can transform them into a binary ratings, like or not like. I can transform them into a Likert scale, like from 1 to 5 stars. I can perturb them in so many ways. So you can kind of redo the exercise when you're changing the quality of the training data in any way you want to see if it's robust. Okay. Another kind of thing that we have to grapple with is, of course, I mean, if I give you a lot of data, you will recover true preferences. Not you know, if I give you a 99% sparse matrix, then you're there, right? So the question is, you know, where do you draw the line? And then here we look at classic data sets. So if you look at the community of those who study recommender systems, you will have some classic data sets. So one is the Netflix competition data set, which is a data set that Netflix released because they try to crowdsource the design of the recommenders. And so the idea is we kind of fix those parameters in a way that reflects the key characteristics of classic data sets in terms of sparsity, number of parameters, number of observation parameter, density, and so on and so forth. Okay, ratio of users to items. Okay, so in the exercise today, I'm going to have 24,000 users and 800 items, but we play with this. Yes.
Questions. So first, the endogenous data versus like you're collecting the data as the algorithm.
So the idea here is, again, suppose you start with no data at all, okay? How do you predict rating? Well, there you just put the average, like 0.5. If a rating is something in between 0 and 1, you would say that, all those utilities are 0.5. Then you make recommendations based on these, which are basically random recommendations, right? Then users report the true utility. Now you're in business, because now for each user, you have one data point, right? You retrain, you see those predictions, you make recommendations, you look at choices, and you have a second data point, and so on and so forth, okay? So you kind of populate the rating matrix. Once it like this, once it reaches a density of 1.2%, we call it a day, and we do the analysis, okay? So we use that training data set to train an algo to make recommendations. We look at what people choose, and we look at what people should have chosen absent those recommendations, and we generate those results.
It's the number. So like the rating factors.
Say that again, sir. Whoops.
You say number of the rating parameters about.
Yes.
Parameters is the number of factors.
It's pretty much the number of parameters in those vectors, t hat and b hat. Yeah, pretty much those two, the size of those two vectors. Yeah. So basically, if you have k factors, k is also, you have to choose how many latent variables you want to allow, and you use regularization techniques to choose that. So we kind of follow the literature. But the idea is, for instance, if k is equal to 2, okay, each user is 2 numbers, how much they like characteristic 1 and how much they like characteristic 2. So each user is 2 numbers, so you have 2 times the number of users, plus each product is 2 numbers, so you have 2 times the number of products, plus a few other parameters. That's pretty much what it is. Yeah. And so, yeah. Okay, that's the experiment. I'm going to describe the experiment and then I'll jump to the result. So in a control, the idea is, suppose that these users, they have a need. All users want to buy one of 19 items, okay? Travel guide. Okay, so there are 19 different travel guides. And, suppose that each user has this need of buying one travel guide. They do not know prices nor their preferences, but they do hold beliefs, okay, about what those prices and preferences are. And then they can acquire information by just drawing those guides at random, right? So which is the process I described. In the treatment, before acquiring information, they're prompted and they say, hey, do you like this travel guide? Okay. When they are prompted, we assume that they realize their match value. So they inspect it. So now they know what the price is, what the match value is, and they have to decide if that is good enough or if they want to keep searching. Okay. We assume that these are rational agents in the sense that they have perfect foresight. So they correctly anticipate what is the value of keep searching. Okay. And they compare that with the value of, buying the recommended product. Okay. Good. So in the first part, this is it. So, if you like your recommendations, you buy it and we record that choice. If you don't, you keep searching. Okay. And then we record that choice and then I'm going to show you what those choices are. So prices play no role. In the second part, I'm going to bring in firms. Okay, so the producers of those travel guides, and the idea is that those producers will set prices, okay, and will do so anticipating what those choices will imply for consumer choices later on. And then the idea I want to show you if prices are higher or lower when you switch on those recommendations. Okay, And then one thing that we don't do, which is by far the most interesting thing, is to think about product design, right? So the idea is, in many applications, clearly these recommender systems, they shape incentives towards product design. Think about social media, right? Those are very important questions. How does the Twitter algorithm shape the content producers' incentives towards providing, more diverse content or higher quality content and things like that? So clearly those algorithms are going to have an impact on those who generate the content, which is ranked by those algorithms. So we don't do that here, but the equivalent here would be, where do you place your product in space when I switch those recommendations on? Okay, that's for the future. Okay, so of course, we don't do this in one run. We run like 100 of those simulations to iron out any residual uncertainty, right? Or noise. And I'm going to report typically either the median figure or the mean figure across all those 100 parallel universes where we do this exercise from scratch. Okay. All right. Yes.
So the assumption is that there is no budget constraint for
There is no
budget constraint for the consumer. They can buy all the products. They have budget to buy any.
Yeah.
And the firms knows that.
Yes. So everybody eventually buys something. That's correct. Or if you want, you could think of one of these options as being the outside option, which is the utility that I would get if I were not to buy, and the price of that is equal to 0. So it's a reinterpretation of this. But let's assume that everybody buys. Yeah.
Just a clarification, like in the treatment, right? The consumer gets the personal recognition, which is the product, not so to say the product attached with the value.
So sorry, I didn't get it.
The recommendation is like really like buy A or B, but not so to say the value attached to A or B, right? It's just so to say.
Yeah, so the idea is that for those 19 items, you take the estimated rating matrix, okay? You rank for each consumer those 19 items, and then each consumer is recommended the item with the highest rating. When this is recommended to you, you learn your true value, okay? This is recommended because it has the highest predicted value. But when it's recommended to you, you learn the true value, and then you decide based on the true value. So if recommendations are bad, you're not going to follow them. You're going to say, this is not good enough, I'd rather keep searching.
I was just wondering in terms of motivation, right? If you think about on Netflix does recommendations now, they tell you like it's a 98% match quality if you watch this movie, so to say.
So the idea is that I press play, I watch the first 5 minutes, there I realize if it's a good match or not. If it's a good match, I buy, so I keep watching. If it's not, I press stop and I go back. Or I watch the trailer, right? I try to gather information on whether this is a good match or not. I investigate it, I click on it, I watch the trailer, I start watching. Then I make an informed decision. Okay, that's the idea. Any other question on yeah?
Store this data, like, does it also record that as like a kind of value in your database?
In the Netflix application, definitely. So here, yeah, no, here, this is a snapshot. So if you want, the data is given, okay, in the baseline exercise, you have two preferences. We build a data set by, say, sampling from those two preferences, and we use that to train. And we look at what they do.
But the train is a binary, or does it have the preferences?
Yes, sorry, I should have mentioned that. So we assume that here you observe the actual rating plus some noise, which is like a random draw from a normal distribution with a standard deviation, which is 0.1, the mean rating. So a small amount of noise, which basically we're saying we're stacking the deck in favor of these algorithms because we're giving them really high quality data. We're giving them a sample, a random sample of true preferences with a small shock. And the reason why I need a small shock is because if I don't do that, then with you know, I think with 50 rating, then you would immediately recover the parameters, right? So we need this shock to avoid this. Right? That's it. Yeah. Any other question about the exercise? All right. So what do these consumers consume with and without? Okay. Now the orange greenish bars, okay, those are that's the world with no recommendations. Now you have 19 products. Okay, so that means that, and this is the case in which we all disagree. So in principle, with perfect information, we would all buy a different thing. So in the baseline, markets, precisely because all these firms, they're all symmetric, market shares are about 5% each, except for those two at the end. Those are the niche firms. Okay, those are the firms that by construction are placed near less consumers than the others, right? So, you know, you should have that these firms should sell pretty much the same amount of items, right? Now, when you switch on those recommendations, you find that, you know, an interesting pattern. So, concentration goes up quite a bit in the sense that if I take the leader, the market leader, the firm with the highest market share, the average market share across those 100 universes is about 16%. So the largest firm is 3 times as large as it should be, both in first best and in third best. First best is what it should be with perfect information. Third best is what it is when we have no information but we search, right? It's 3 times as large. Now, this is the market share. I should have mentioned. These are the market shares of these 19 firms, ordered by popularity. Okay, so 1 is the average market share of the largest firm in those universes, and so on and so forth. So look at, you know, the poor guy 19, 18, 17. I mean, those guys are the guys who are complaining and they're saying, hey, it's not that I'm not selling because my product is not good. I'm not selling because I'm not recommended as much as I should. Okay, so somehow these guys, well, those guys, they enjoy they enjoy the favor of the algo. Those guys, they're penalized by the algorithm, right? You see that, right, from a competition policy perspective, this is a problem, right? There is no reason whatsoever why those guys should have a market share which is 1/16 of the largest guys, right? So this also speaks to the question of if you want to think about other contexts, the diversity of consumption, right? Consumption is much less diverse with these algorithms than it is without. Okay, and that's a problem in itself, right? All right. So recommendations are good and biased. So another important aspect is it's not that recommendations are bad. Recommendations are good in the sense that on average, we do consume better products when I switch those algorithms on. It's just that, you know, maybe rather than me getting recommended my first choice and Tobias being recommended his first choice, we're both recommended the same product. So, you know, and if you do this for a large number of users, then, you know, we're all pretty much consuming good products, just not the products that we should. And on top of that, some of these products are overly recommended. Okay, that's what we're trying to document here. Yes?
What's I missed the logic for why you know that this is, maybe those firms are good products that are just like satisfying.
Because I design preferences. So preferences are designed. So I know exactly what should be recommended according to true preferences. Okay, so I designed them in such a way that under full information, we should all know. So these firms should sell on average to 1/19 of the population with this twist of the niche ones. And so that's how I can identify the bias. That's actually crucial right here. So what I'm trying to push this idea that when you use these economic models, then you identify the bias. If instead I were doing this with some data or with some Monte Carlo simulation without the economic model in the background, if I observe a firm which is selling more than some others, how do I know if that's the case because of consumer preferences, maybe this firm, you know, how do I know that Amazon Choice products are not just better, right? If I document you that Amazon Choice products, they have a higher market share, is that because the algorithm is favoring those products, or is that because, you know, maybe they're just better? So is the algorithm cutting to preferences or not? So that's it. Yes.
I'm wondering if you tested the other ways. So if I understand correctly, here the benchmark is random recommendation, essentially.
No, not really, no recommendation. The benchmark is that you randomly sample. Yeah.
And then the blue one is personalized recommendation, right? But there seems to be like another natural choice, is like popularity-based recommendation. So
yeah.
So I'm wondering, like, the consequence of that probably will be worse, right? Like,
Yeah, so that's something, yeah, I agree. So that's what we should be doing. We haven't done that yet, but that's definitely something that we should be doing. So ranking by popularity, and see another way of thinking about endogenous data or endogenous issues is, yeah, we don't do that.
because we know from this market, music market experiment that basically there, if you rank by popularity, you get this kind of fact that randomly people pick one.
Yeah, so ranking by popularity requires a process, right? Because you want to have a process in which by chance, a firm gets popular, and then you see if, there is this get richer effect down the road. So again, this is just a snapshot. So, but yeah, I agree. It's super fascinating.
Just in terms of timekeeping, maybe like the very important question that we still have some time for questions at the end, maybe that Emilio can finish the next 10-15 minutes.
Yes.
Is that possible?
Yes.
15
yes.
slides.
Yeah. Sorry.
And then to have some time at the end as well. Yeah.
All right. So this is where I show you where this is the how we try to show you that this is really a problem of the algorithm and not of the data, because we do the same exercise by using the endogenous data I described. Okay, and then we find pretty much the same pattern. So in the sense that endogenous data tend to exacerbate the problem, but it's clearly not the main driver. Okay, if you think of this lack of diversity or concentration being an important issue. Okay. So next, of course, we were asked, since this is an algorithm problem, how can we actually try to understand what's going on? Okay, that's a difficult question to answer. So we have to become creative to answer that question, right? Because, one way of interpreting this exercise is I have a statistical tool whose goal is to estimate some parameters. And I just showed you that this tool has systematic biases in those estimates. Okay, these systematic biases means that, some firms imply that some firms will be recommended more than others. And then the question is, can you eyeball what those systematic biases are? And the simplest thing that we could think of is, I can, in the case, so this is the case in which you have two dimensions, okay? So remember, one item is a pair of numbers, one user is a pair of numbers, and the idea is we're just gonna plot both the true location of those item and users and the estimated location of those item and users, right? So I have item and users in subspace, and I'm estimating their location, and then I just look at, if I can discern a pattern by looking at that. And this is what this exercise is trying to do. So here, both item, so this is, the case in which you have two factors, okay? So every user is just a point on the Cartesian plane. And in this exercise, users are spread over the unit circle by design. I put them on the unit circle, equally spaced. I put products on the unit circle, equally spaced. Because of this geographical interpretation, for instance, the guy that sits on the 45-degree lines will strictly prefer the product on the 45-degree line. And so as he travels along the unit circle, his match value will go down. The more he travels to find the product, the less the utility. So the red circle is where products and users are. The yellow cloud is the estimated users, and the blue, it's not a cloud, this blue set of points is the estimated items with the market share as a disk. Okay. So what we were showing here is what we call the homogenization and massification of preferences, which is that the idea that the yellow cloud is pushed. So these users are estimated to be closer than they actually are, and closer to the 45-degree line than they actually are. Okay. So the idea being is that this algorithm, if I look at the estimated preferences and I compare it to the true preferences, they're more homogeneous. So the algorithm thinks that we're similar to each other than we actually are, and they're closer to the center, which is where market share is highest. Okay. So that's one thing that we document. Another thing that we document, which is driving a lot of this, is, in this model, characteristics are good. So if you move northeast, utility increases. So if you move those products in the northeast direction, everybody likes them more by construction. And so one thing that we document is that there are tiny variations in the estimated distance from the origin. So some products which by chance are estimated to be farther away, they steal a lot of business from nearby products. So a lot of that concentration is also due to the fact that some product by chance, they get the favorable estimates and then they recommended more as a result of that. Okay, well, that's one way of doing this. So I guess there are better way of doing this. Okay, now let me bring in prices. Okay, so here again is the same exercise, but before those recommendations take place, I allow firms to pick a price. Okay? And I look at prices with and without. Right? And so basically what we show here, these are the results. Let me jump to the results. These are the prices of those 19 goods I was showing you before, arranged according to their location in space. Okay, so the mass goods are at the center, the niche goods are at the edges, and so here you're looking at the prices without in yellow, without recommendations, and with recommendation in blue. Okay, so basically what we show is that once you start recommending, prices go up quite a bit. They increase by 25%. And then, of course, you might ask, why are firms pricing higher when consumers are directed, right? So this is my way of trying to build intuition, and then I'll conclude. So this is invest demand, okay, price and quantity. Okay, this is the invest demand that the firm who's in the middle faces when there are no recommendations. Okay, if you lower price, you sell more. Invest demand in the benchmark. So that's the world with no recommendations. So what happens when I introduce those recommendations? So first of all, this thing shifts up. Demand shifts up. What does it mean to shift up? Well, it means that for the same price, you sell more. Why is that? Well, because of course, now there is an engine, an algorithm, which is directing users that like my product towards me. So the willingness to pay of my customer goes up mechanically, right? So this is kind of a mechanical effect. The second one is subtler. So demand is kind of shifting counterclockwise. So the idea is that I'm facing a more homogeneous population, right? So before, as I was lowering my price, I would bump into consumers who like my product less and less. So here instead, those who are directed towards me are much similar to each other. So this counterclockwise rotation is very important because it's making demand very sensitive to price changes. Now, because everybody has the same valuation, if I change the price a little bit, demand shifts by a lot, right? Because all those consumers, they have similar valuations. Another thing that happens due to these tools is that this kind of thing bends in. And the idea is, if in the old world, suppose I was selling, by analogy, a guide for payments, no? And suppose there is a single who's searching. In the old world, if I were giving the single a low enough price, eventually it would kind of settle. It would say, sure, maybe the Lonely Planet is better for me, but Lonely Planet is 30 euros, this one is 2. I'll settle, I'll buy this one, okay? In the new world, you don't see those customers anymore because they're directed towards their favorite product. And so no matter how much you lower your price, you're never going to sell to them because they're directed towards my competitors. They buy my competitors' product. So by lowering my price, I'm not getting that demand anymore. That makes sense? So all in all, we show that these effects combined, they create, if you want, market power. So now, precisely because these guys that like me are directed towards my product, I'm able to charge a higher price. So I'm less sensitive to competition from my rivals. And so this kind of personalized prominence has like this downside of inducing higher prices. Okay. here we try to kind of compare these two effects. Yeah, we're thinking about welfare. So is this a good thing or not to switch on these recommender systems? On the one hand, they're an incredible source of value because people buy products which are a better match for them. On the other hand, they get extracted, right? So prices go up, so they pay more for those better products. Now, which one kind of prevails? And we show that all in all, surplus goes up in the sense that these like higher match values are less than compensated by the higher prices. Okay, so the last point, I'm just going to skip this. I'm just going to tell you that because we can play with the quality of the data set, I can show what happens to consumer surplus as I move in quality. And so it's actually a hump state. We document that consumer surplus first goes up when you provide better quality data because of that, better matching. But then eventually those benefits level off. So the marginal value of better data eventually levels off when those recommendations are really good. And you just have the bad effect of inducing higher prices. All right. So there is really no policy message in the sense that this is a very crude exercise. So you can hardly distill any policy lessons from this. If you really wanted to take it seriously, you could say that all in all, recommender systems are good, okay, in the sense that they induce better choices, despite the fact that they induce higher prices. But I guess the idea is, what I'm trying to tell you are not the results of this experiment, is the method. I'm saying, okay, you don't like this class of algorithm, you pick your own, right? You don't like this preference structure, you pick your own, you pick something which is a good fit for the application. But I guess this is kind of informative of those kinds of questions, like should there be this concentration or not? Is this concentration an artifact of an issue with these tools or not, right? Yeah, I guess, yeah, thank you.